Hi, welcome to our latest episode of the ConnectNext series. I'm Corey Collins with First Line Technology, and I'm joined today with Chris Hodge. A lot of you may know Chris. If you don't, Chris is a developmental chemist. He's a formulation chemist. He's got over 25 years working in decon sciences, and Chris has forgotten more about decon chemistry than most of us will ever know. I learned a lot just by talking to Chris and our conversations that we have, and he's been nice enough to come and join us for this series and share just a little bit of what he's learned over his decades of experience developing for decon. One of the other things that Chris is known for, I guess one of the big achievements, is he was one of the primary developers of Dahlgren Decon, which of course is a three-part decontamination solution. And the microemulsion component, the surfactant component, which is what he's going to touch on today, is a very, very, very important part of that decontamination system. So we're going to have this presentation Chris will present. You're going to be able to ask questions anytime throughout the presentation using the Q&A function. And at the end of this, we'll have about 15 minutes where Chris will be able to answer your questions live. So Chris, take it away.
Thanks, sir. All right, so decon formulation in some ways is pretty straightforward, but the foundation that it's built on is pretty complex. So what I talked to Corey about was putting together some foundational pieces where we talk about things, components, concepts that can be assembled later for the big picture, but we're going to focus on some fundamentals today and maybe through a couple of these episodes, and then bring it all together one day out in the future in another episode. To begin with, I wanted to talk to you a little bit about water. So, ultimately we're going to talk about surfactants today, but what we're acting on with the surfactant is typically in a decontamination scenario going to be water. So water's a very unique compound. Beyond being the most abundant compound on the planet Earth, it's the third most abundant compound in the universe. We're all familiar with it. We're somewhere around 70% water ourselves. It is odorless, tasteless, has very little color associated with it. A lot of times it'll have a blue appearance because of how it interacts with visible light, but otherwise it's clear. A lot of times you'll hear it referred to as a universal solvent. That's true in some cases. It dissolves more things than just about anything else, but it doesn't dissolve everything, and we'll talk about oil and water not mixing and things like that later. But water in and of itself is unique beyond its credits, right? It has unusually high melting points and boiling points. It has very high surface tension. It's known for having, or we take advantage of in a lot of different fields, the fact that it has, or has capillary action. It becomes less dense as it freezes, right? Pretty important to life on Earth because ice floats. Otherwise, we would freeze everything and nothing would be able to survive in the ocean. It also exists, the only compound that exists as a solid, liquid, and a gas on the Earth's surface. So lots of background information about water. But now why? Why does it have high melting points and boiling points, and why this unusual surface tension or high surface tension? And to really get into that, we need to talk a little bit about the forces, or the construct of water and the forces that all materials have in relationship with each other. So those cohesive forces, those things that attract things together. So what you see here are a couple of chemist depictions of water. You might be more familiar with designations like H2O, right? Or seeing it drawn differently, right? Two H's and one O connected by a couple of lines. But interestingly, right? And again, this is the way I kind of see the world, three-dimensional pictures of stuff. It's not just two hydrogens and an oxygen. You have to take into consideration these lone pairs, right? That's just a pair of electrons hanging out on one side of the water molecule, right? So these bonds, right, between the oxygen and hydrogen are a shared pair, a covalent bond, two electrons that reside between the hydrogen and oxygen. And if you think about hydrogen on the periodic table, it has it's way up in the top left corner, right? One proton, one electron. So that means that its only electron is spending more time on the oxygen side than anywhere else around. So kind of have a naked proton sticking out of the back here. So you get kind of a net positive charge on one side of the water. And over here, you've got a couple electrons which are negatively charged. You get a net negative charge on this side. And so what you wind up with is a molecule with charges on either end that are opposite. And we think about that as being polar, right? It has a positive charge on one end and a negative charge on the other end, or vice versa, depending on where you're standing here. So why is that significant? Well, later we'll talk about things related to polarity and non-polarity and how substances interact. But for this discussion, when you have something that has the positive charges kind of hanging out on the back and hydrogens are special, you wind up being able to get interactions between these two things. So the hydrogen on one water molecule can associate with the electron pair, the lone pair on the oxygen, and create what is known as hydrogen bonds. Right? It's stronger than van der Waals forces, which is another term that describes the energy that everything has in relation to attraction to other molecules around it. But it's not a covalent bond like between the hydrogen and the oxygen. It's a special and very unique thing. It's fundamental to life and all kinds of stuff that are dealt with in other fields. But this is going to be a big factor in all of that stuff we talked about, the high melting point, high boiling point, the strong cohesive forces, strong surface tension. And it becomes an important thing to manipulate to take advantage of for the purposes of dissolving things and decontamination. So we mentioned that we might want to interact with or manipulate those properties of water, like surface tension. And so how would we do that? And that gets us to the point of the day, right? Surfactants. So what are surfactants? Well, if you just break down the word, it comes from the terms surface active agents. So it's just kind of a glom of those words to create a term that's, right, because chemists like to abbreviate stuff. We don't like writing stuff out. It is just compounds that have activity at surfaces, okay? And so part of the reason for that is surfactants are what's known as amphiphilic, right? It means they have a duality of their nature, right? So they have, and you remember this term polar, they have a polar head or end and a non-polar tail, okay? This is kind of significant, all right? We talk about surfactants in terms of loving water, right? Hydrophilic, hydro, right? That's kind of a Latin word for water. And philic or hydrophile is something that likes water, loves water. And hydrophobic means something that hates, right? It is water, and there's a hate for it, right? This is a love. So you can kind of flip around the terminology a little bit and say that this is lipophilic, right? You may see something like this later. Lipophilic, spelling again is hard. This means, right, fatty loving or oily loving, right? Another term we use for nonpolar is oily, and another word we use for polar is aqueous. All right. So, when we talk about, I introduce a lot of terms because as we talk about stuff going forward, as we talk about surfactants, we're going to use a lot of this stuff interchangeably, and now you've got kind of a roadmap for the terminology. All right, so now that we've kind of walked through the fundamentals of what a surfactant is, what's something maybe that you'd recognize other than like a picture and a bunch of Latin words? So what are surfactants, right? Think soaps or detergents, right? Things that you use routinely in the home: shampoo, dishwashing detergent, laundry detergent, right? And why do we use that? It's because we have oily things, dirt, grease, grime, right? Think contamination, that we want to somehow get in something that we all have in our homes. Water. We want to get this oily contamination into an aqueous system, right? We want the dirt to get off of us or our dishes or our laundry and into the wastewater. And so we use surfactants every day, right? These are well-established materials that all of us are much more familiar with than we realize. All right, so let me tell you a little bit about surfactants. Over here, you've got a picture of some polar heads, right? Polar. And some non-polar tails, right? Oily, aqueous, hydrophobic, hydrophilic, all that same kind of stuff again. But let's go a little deeper, right? So we've got these, right, that have charges on the ends, right? See those charges? Minus, plus, and minus. These are what we refer to as ionic surfactants. So these are surfactants with real charges at the end, so ions. This type is non-ionic, right? The head is still polar, like water's polar, but doesn't have an ion. Doesn't have a charge. This is the same. It is polar, but non-ionic. Down here, in these ionic ones, we have the negative, right, which is an anion, so we call it anionic. This is actually the most common type of surfactant that is manufactured in the world. About 50% of the surfactants that are produced are anionic. This is cationic, right? Cation is a positive ion. And then this one, start getting into those big words again. This is referred to as Witter-ionic. And it just means that you have both positive and negative charge in the same polar head. All right? So why is that significant? Or why is it significant that surfactants have polar heads and non-polar tails? Well, it turns out that surfactants are attracted to interfaces, particularly the air-water interface. So if you think about, there was an old TV commercial for, I believe it was Dawn dishwashing liquid, and they had a sink full of dirt and grime, dirty water. There was a film on the surface, and they put a drop of Dawn into the dishwashing liquid into the sink, and everything parted, right? And that was the dish soap coating the surface, and that's how fast it is, really fast. So surfactants are attracted to interfaces, and they have an effect on the interface, right? This is for a decon chemist or a formulation chemist or an interfacial scientist. This is fascinating stuff. Spend a lot of time here. A lot of benefits that come from this phenomena. Now, they have attraction to other interfaces as well, and we'll talk about that a little bit more later. But this phenomena is really critical when you begin to talk about surface tension and the reduction of surface tension as you mess with the cohesive forces that hold liquids together, right? So it's true in water, which is what we're going to talk about, but it's also true in other liquids. So again, water has an unusual surface tension because of those strong interactions that it has with other water molecules. But being able to get things that disrupt those interactions, those cohesive forces, both at the surface and throughout the bulk, is critical at manipulating surface tension in the systems that we're interested in. Okay? So, as an example of a visual of surface tension and the effects that it has, I'm going to throw out a couple of terms here. There's one that is like dissolves like. Right? This is an old chemist adage, but a lot of people have heard it. Right? That means, right, polar things will dissolve polar things. Water dissolves salt. Oily things will dissolve oily things, right? Gasoline will dissolve grit and grime if you work on an engine, right? I think we used to use benzene to get grease off of parts. And we can form emulsions, right? So think salad dressing, right? That's probably the best picture, Italian salad dressing of a simple emulsion. You take vinegar, which is mostly water, 5% acetic acid, and 95% water, and olive oil, and you put them in a flask or a bottle, and you shake them up, and you form an emulsion. You have droplets, right? And it doesn't stay mixed, right? When you shake up an emulsion, you add a lot of shear to it. The droplet gets smaller and smaller depending on how hard you shake. But eventually, if you set it aside, it'll separate again. All right, so emulsions, by and large, are not permanent, right? And part of that is because another phrase that we use all the time, right? Oil and water, probably seeing it in the background, don't mix, right? And again, it comes back to these cohesive forces. Oils like to be with themselves, right? They like other oil. Water likes to be by itself, right? It likes to be with water. And they don't mix. So how can we affect that? And what do surfactants have to do with it? So sometimes surfactants are called emulsifiers. So they help facilitate the formation of emulsions. And again, it comes back down to stuff happening between or at the surfaces and between the molecules in a system where that cohesive force is lowered, right? And you reduce the energy that's required to form a mixture. And depending on the type of emulsion you form, they might even form automatically, right, naturally. So I'm going to expand on the picture that we had earlier a little bit. Right, what if we had another layer instead of just air? What if we had an oil, right, or an oily layer? Well, guess what? Surfactants still like to be at interfaces. So they will first line that oil-water interface, and then they'll begin to line the container at the solid liquid interface. And and then they'll begin to accumulate in the bulk. All right? So it doesn't just happen automatically that you begin to get surfactants in the solution. It turns out that you line all the surfaces first, right? Remember, again, the Dawn dishwashing liquid example. The whole surface was cleared before anything really started doing anything differently. And then at some point, when you keep adding surfactants, you hit what's called the critical micelle concentration, or you get enough soap in it that they begin to aggregate, build up in the bulk. They begin to increase in concentration in the bulk, right? Think bulk, right? The whole system. And then when they start adding up here, they begin to aggregate and form what we call micelles, right? So the concentration at which those start to form is called the critical micelle concentration. All right, this becomes critical for things we're going to talk about. So micelles. What is a micelle? Well, a micelle is simply a group of surfactants that are in a sphere inside a liquid, and they have the oily tail and any oils in the droplet now inside. Right? And your polar heads out here, right, insulate it from the bulk. So is this always true? Well, in fact, you can have the opposite, right? You can have a water and oil, right? This is a oil in water micelle, and you can have a water and oil. You can have the opposite. So to show that a different way, I can have an oil in water, right? My oil is on the inside. Or I can have a water and oil, right? That you just turn it around the other way. You have to design these so that it'll work, but you can do it. If you use a more sophisticated approach, you can actually drive a combination of these into continuous bilayers or continuous layers. And this is called the bicontinuous phase. So in this case, you would have alternating and even moving oily and water type of layers. And your surfactants would align themselves in these layers. So you can imagine that you would have polar heads in the aqueous or the water layer and the oily tails off in the oily layers. All right? So whether you're looking at it like this or like this, which isn't as pretty, you're still getting the same concepts where you're separating out your oil and water. Or you're bringing the oil and water closer together. Why is that important? Because most of the chemistry that I want to bring into the context of contamination is in the aqueous phase. And most of the contamination that I have is in the oily phase. So if my oily phase is my contamination and my water phase is my chemistry, I've got to get them as close together as possible. And this kind of construct here allows me to get much closer than here. So it's all about turnover, right? And I talk about chemistry being a contact sport. If I can't get the molecule I want to react in contact with the other molecule I want to react, I can't do chemistry. So I want to get my materials, the chemistry I want to do and the contamination I want to do it to, as close together as I can. Now, I want to kind of introduce some terms that that come into play when you start thinking about formulations or emulsions this way. We talked about the term emulsion, right, which is just a mixture of two unlike liquids. Then there's a term called microemulsion, all right, and it's a little different. It's special. In fact, you can generate these bicontinuous layers by designing microemulsions. So emulsions, right? Remember those big droplets we had in salad dressing, and we talked about dirty water and stuff like that with sink and laundry. Emulsions tend to have particle sizes of about 1 millimeter, right? Those droplets, and that forces them it forces light to interact with it. So when you look at an emulsion, it doesn't tend to be clear. It tends to be cloudy or even opaque. Whereas microemulsions have particle sizes, or some of these particle sizes, of 1 to 100 nanometers. Okay? So we'll talk a little bit more about that as we go along. But the microemulsions are unique and stable versions of emulsions, which is something that we're very interested in decontamination chemistry. Because microemulsions are clear, they are thermodynamically stable, and they're, since I'm doing big words, they're isotropic, right? So thermodynamically stable just means that they're temperature stable. If you form one, it'll be stable across a wide range of temperatures, which isn't always true of emulsions. They're isotropic. It means they're uniform throughout, right? Especially if you have this kind of structure. I'll show you a better picture of this later. But they are also very well dispersed. So those layers, right, are very thin, and your chemistry is intermingling rapidly. All right, so this is a picture, kind of, if you will, an artist's rendition of the bicontinuous phase microemulsion that we used for Dahlgren Decon. And you see here in this area, it talks about it being lipophilic, right? Remember, that's oil loving. That is where our contamination or our agents reside. You see here in this area, these white layers, that is our hydrophilic area, or where our aqueous layer, where our chemistry resides. And because we've got this structure the way we do, we get them a lot more closely intertwined. So we developed a microemulsion system for Dahlgren Decon to help bring those two things together. Now, microemulsions are a term that originated a very long time ago, back in the 40s, I think 1943, a couple of professors at Cambridge University, Hoare and Schulman, and they did a lot of studies on these, right? They identified that the particle sizes were 1 to 100 nanometers, and they did work related to determining the temperature stability and all of that kind of stuff. But some of the important things that came out of that were the fact that these can be self-mixing, right? They form naturally. So if you put the things together that form it, you don't have to add energy to the system like shear. You don't have to shake it. It'll automatically form. But it has some interesting properties, right? It has amazingly low, they talk about it as ultra low, interfacial tension. Right? Think surface tension. Remember we were talking earlier about how surfactants disrupted those cohesive forces? and that had benefits in terms of getting things to mix, stabilizing emulsions, and getting your chemistry to interact. Microemulsions had the benefit of generating extraordinarily low interfacial tensions, right? And they also were able to generate methods for developing the microemulsions using various types of surfactants and oil and water, water and oil combinations. Recently, another term has begun to pop up, and that's a nanoemulsion, right? So what's the difference between a microemulsion and a nanoemulsion? If you remember, we said our particle size here was 1 to 100 nanometers. You might think with a different name that it would be different, but it's not. The particle size for nanoemulsions is also 1 to 100 nanometers. It turns out the only real difference between the two in terms of how they're defined is the fact that nanoemulsions are not temperature stable. And for the applications most of them are designed for, that's not a problem because they have to operate in very narrow temperature ranges. But for the purposes of decontamination, your gold standards of microemulsion. Nanoemulsions are heavily focused in the pharmacology world for drug delivery and things like that. But that is pretty much what I had today with respect to surfactancy, and the concept of formulation and formulation for decontamination. So thanks for having me.
Awesome. Thank you so much for being here, Chris. That was great. We'll have about 15 minutes to do some question and answer. Before we get into that, I just want to mention this is just the first in a series. So a lot of this was defining terms. I think a lot of folks in the hazmat community think soap is soap is soap. And you can mix soap and oxidizers and it doesn't really matter. But one of the things I've learned from you and just today is talking about how those things do actually matter, and choosing the soap for the threat and choosing the soap for your conditions really does matter. Yep. So we'll kick off into our live question and answer session now. Thank you.
See you there.
Okay, so unfortunately, we're having some technical issues, as you may have seen, with this broadcast on our end, getting Chris on live as a presenter. We do have some questions. What we're going to do is we'll actually have Chris answer those questions, and we're going to send out a email later with a better quality link to this stream if you had issues watching it when it happened, and Chris will be able to answer all the questions we have. And we will definitely promise to get some of these tech issues resolved before the next one. So for everyone that did attend, thank you for your time. Chris, I know Chris is actually watching this as a viewer. Unfortunately, he's not able to get on live as a presenter. So Chris, thank you very much for your time. Great information, and hope we catch you guys next time. And to keep an eye out on your email for a link to the QA and a copy of this stream. So hope everybody has a great weekend. Thank you.